Building Information Modeling, BIM, is the process of constructing a three-dimensional representation of the physical and functional characteristics of any built structure to allow better planning, constructing, and operating a structure. Traditionally, the construction industry relies on a vast range of documents during construction, such as 2D drawings, bills of quantities, BQ, and programs. All of these documents are used to represent one element of the project with reference to the previous examples: design, cost planning, and activity scheduling, respectively. This approach greatly hinders the construction process, as parties would have to dig through multiple documents in order to obtain a fuller picture of the project. BIM is a process that could combine all these elements, depending on how many dimensions it has. A 3D BIM model is the most common model used currently. It is a three-dimensional representation of building design, showing the spatial relationship between different components. This allows an easier and quicker visualization of the building design. By utilizing features such as clash detection during the design stage, feasibility issues and design errors could be spotted early, potentially minimizing the risk of errors and rework. A four-dimensional BIM model is a 3D model that also incorporates time in the visualization, where the construction program is included into the model, linking all building components to the scheduled construction sequences. This enables the project planner to visually inspect the workflow, allowing a simpler process when identifying possible logical flaws in the program, rectifying these errors before construction commences, ultimately reducing risk. A 5D BIM is a model that adds one more dimension to the 4D model, infusing cost-related information into the model. This is possible by modeling with quantity and cost data of every construction trade, such as concreting, reinforcements, fire services, finishes, etc. A 5D model is beneficial to the cost planning process, where it provides a potentially more accurate quantity takeoff to each component, while also requiring significantly lesser time when comparing an amateur of both methods. In Hong Kong, BIM is promoted by the government. HKHA has applied BIM since 2006 along the building life cycles, from design to documentation, construction, and facility management. For example, at the planning stage, by the integration of the implementation of BIM and GIS, site appraisals and visual impact assessments in the 3D GIS environments are performed to minimize the visual impacts of the development to the environment. On the other hand, the government understands that the private sector may not be familiar with BIM, and therefore, in order to aid the construction industry to adapt to the new technology, HKHA published standards and guidelines for BIM implementation. Virtual and Augmented Reality (VAR) is the combined term for virtual reality (VR) and augmented reality (AR). VAR is a technology that creates an artificial environment and allows the immersion of the user to interact and experience within this reality. Virtual reality refers to the complete immersion into a virtual environment, where the simulated experience could be similar or completely different from the real world. Virtual reality could be delivered by two distinct methods: simulation-based and projector-based. Simulation-based virtual reality is the most well-known form of VR, where the user is brought into the virtual environment using a VR head-mounted display (HMD) device. For example, the HTC Vive VR headset. A HMD device usually includes two high-resolution monitors, binaural audio systems, and real-time head tracking. This is crucial to the interactive experience between the user and the simulated environment. Common non-construction applications of simulation-based virtual reality would be for military training, medical training, and astronaut training. Virtual reality is important for these types of training, as training in their actual environments could be too risky or costly, whereas VR provides a more effective alternative. VR gaming and videos have also become increasingly popular lately, showing VR's capabilities for entertainment purposes. Projector-based virtual reality is a type of VR where the projector uses 3D projections into a cave-like environment. Lightweight 3D glasses, similar to commercial 3D movie glasses, will be utilized to bring the projections into a three-dimensional view for the user. This type of VR has a more limited immersion than simulations, as the user could not be fully brought into the virtual environment. Interacting with virtual elements could be conducted through wireless handheld controllers, similar to simulation-based virtual reality. Projector-based virtual reality is most commonly used for pure visualization of environment due to its limited immersion and interaction options. Augmented reality, AR, walks the fine line between real and virtual environment, where virtual elements are brought into the real world. Instead of immersion, augmented reality aims to enhance the real environment by providing additional information, such as holograms or the ability to see through structures. The lowest level AR could be brought by smartphones. Social media platforms such as Instagram or Snapchat have been utilizing AR technology in their cameras. Higher level AR would require HMD devices such as the Microsoft HoloLens, with more accurate integrations and interactions of virtual elements. Augmented reality could be used in archaeological research, where possible archaeological features of ruins are displayed onto existing ruins. STEM education have also been utilizing AR in teaching, where students could directly interact with the knowledge they're learning. For example, visualize and interact with the spatial structure of molecules or physical simulations. The potential and capabilities of virtual and augmented reality is far beyond the previously discussed functions. VAR is a technology that could significantly enhance the time, cost, and quality of constructions when combined with BIM technology. This section will discuss a few notable applications of virtual and augmented reality as an extension of BIM. Virtual reality assisted design. During the design stage of projects, the traditional distribution of roles between parties, either the architect or design consultant is responsible for architectural design, designing for beauty, while an engineer is responsible for the feasibility of these designs on a practical standpoint. Although there are design meetings between the client and the design team, it has been a common practice to have discussions centered around 2D drawings. While elevation, section, and detail drawings could provide a fuller picture to the design visualized by the architect, the client is still forced to rely on his own imagination on the architect's design. It has been a persistent problem where such reliance on experience and imagination have led to misinterpretations from both parties, causing different expectations of the final outcome, which would be discovered at a later stage of the project, usually when mistakes have already occurred. Such mistakes could lead to negative cost, time, and quality impacts to the project. The implementation of BIM models have been proven to reduce these misunderstandings, as the architect could better convey his design, while the client could easily visualize the actual design instead of by imagination. This, however, is not the full potential of BIM-assisted designing. Although BIM models displayed on computers allows full visual access to the design structure, the sense of scale is difficult to grasp even with the assistance of adding a simulated user to the model. Details are also difficult to view on BIM models, as computerized BIM controls are still not as fluid as actually walking in a building. The incorporation of VR into the visualizations of BIM models could greatly enhance this experience by providing better immersion into the actual design environment. Iris VR is one example of VR-assisted designing. Together with cloud-based sharing technology, Iris allows multi-user meetings, where different stakeholders' representatives could enter a BIM model and inspect the entire design. Iris allows the user to add annotations and comments directly to the model, virtual measurements, filtering the model by layer during inspections, etc. Augmented reality assisted BIM walkthrough. Virtual reality assisted BIM walkthrough is a component of VR assisted designing, but this must not be mistaken with augmented reality assisted BIM, as their target user and benefits are different. While VR in BIM is more commonly used in meetings and office environments, AR-assisted BIM walkthroughs aims at enhancing on-site inspections. AR is best used on-site for building services and temporary support work inspections, as clashes in architectural or structural models are more easily identifiable in computerized BIM. Building services such as pipes and conduits are difficult to inspect purely on a virtual model. During on-site inspections, augmented reality HMD devices could allow the inspector to see either holographic displays of planned components or inspect built components using thermal vision. This would allow an accurate understanding of clashes and obstructions that would otherwise be more costly to identify by traditional methods. BRE Smart Helmet is a technology that incorporates augmented reality into the on-site inspections. This technology consists of a hard hat and an AR display visor. BRE is capable of holographically displaying components of building using GPS, tracking the user's location and matching the displayed information with the BIM model. BRE is also capable of thermal vision, giving a user the ability of capturing infrared pictures and videos of elements that would otherwise be difficult to inspect in a non-destructive manner. VAR-assisted designing. VAR technology is also useful for temporary support designing. This refers to elements such as struts and king posts for basement construction. During excavation, Temporary support must be implemented to prevent site collapsing. Accuracy of designing temporary support is hindered by the lack of information of underground conditions, as soil reports are not sufficient enough to provide a full picture, leaving complete designs until excavation work commences. BIM model allows the user to design temporary support by assumptions before actual excavation. Virtual reality could allow visualization of the temporary support design against the superstructure, while augmented reality would allow visualization of the design against the actual site, adjusting the design based on site conditions instead of forcing contractors to make immediate on-site changes. Avoiding rework caused by misunderstanding of design. Clients could understand the design of building easily when VAR is adopted. In general, only 2D drawings will be available at the early design stage. However, clients may not be familiar with the construction industry, such that they could not understand the drawings well. With the implementation of BIM and VAR, the building designs can be visualized. The client could understand the design easily, even if he is not equipped with construction-related professional knowledge. This could avoid misunderstandings between the client and the architect. The possibility of rework due to building designs can also be reduced. Borowski found that the mean of rework costs were 5.5% of contract value. From the rework costs, 50% was direct costs, 32% was indirect costs for main contractors, and 80% was indirect costs for subcontractors. Also, rework can cause an increase of the original project duration up to 77% according to WASFI. And therefore, visualization of building designs could reduce the possibility of rework that incurs extra costs and time. Monitoring building services system during in operation. VAR technology can visualize real-time data, which enhances the efficiency of on-site inspections. With an augmented reality HMD device, the inspector could obtain information on the top of actual work environment. For example, when an inspector wants to check the condition of water pump and tank, he could use an AR HMD device, which could identify and display the pressure of the pump instantly and accurately. Efficiency of inspection work could be enhanced. High cost. High-skilled BIM technicians are required for the implementation of BIM with VAR. As VAR is a new BIM extended technology in Hong Kong, those experts are rare. It is costly and not easy to hire them. Since the adoption of BIM and VAR incurs extra costs, it is seldom used in Hong Kong's construction industry. Requiring complete designs. The implementation of VAR technology for visualizing building designs requires the completion of building design, such that the actual building design could be represented accurately. However, in real practice, due to tight schedules, it is often that construction starts before the completion of the whole design. Variations of building designs after commencement of work is also common in Hong Kong. Therefore, the BIM model may not be accurate. Updates of the model from time to time may be required. Slow adaptation of new technology in Hong Kong construction industry. Psychological resistance to adopt new technology is one of the main challenges. The implementation of BIM with VAR technology requires practitioners to be familiar with all these new technologies. Additional training may be required. This requires extra efforts and breaking old habits. Most practitioners in Hong Kong have reached a certain age where it is commonly found that they resist learning new things, and therefore, the adaptation of new technology in Hong Kong's construction industry is low. A low level of software compatibility. To apply VR technology with BIM models, it is common to use Revit for modeling and Unity for visualizing them in VR environments. However, there are compatibility problems, though they are designed to be interoperable with each other. Details such as material data would be lost after exporting the model to Unity. Policies. In Hong Kong, BIM is adopted in development projects, fundamentally because of mandatory requirements from the government. The Building Department first issued a practice note to encourage BIM adoption in building projects under the Building Ordinance ADV 34. However, it's only advisory. After that, the Technical Circular Works No. 7, 2017, issued by Development Bureau, further instructed BIM adoption for projects in the investigation, feasibility, planning, design, and construction stage in the Capital Works program. But this technical circular only made a small portion of BIM adoptions majorly at design and construction stage mandatory, and therefore it was later replaced by Technical Circular Works No. 18, 2018, where more BIM adoptions at both design and construction stage become mandatory. Currently, those BIM requirements only apply in government projects. Extending such requirements to private projects can further enhance the promotion effect. Specifically, The building department might require the authorized person to submit proving documents of adoption of BIM in the process or application for occupation permit. Since the industry is forced to adopt BIM, they have the intention to develop extended use of BIM like VAR, because such extended use maximizes the benefits and efficiency of BIM adoption. To encourage more types of extended use of BIM, BIM adoption in more aspects should become mandatory. Yet, establishing extended use directly as mandatory requirements might not be feasible, since BIM itself could already be an unfamiliar technology to some companies. Moreover, there are a large variety of BIM extended uses, and different companies might only specialize in some of these extended uses. Therefore, it is recommended that the buildings department might only set those uses as optional requirements at the moment, until some extended uses become mature and broadly publicized. Trends. Comparing the BIM use listed in the old and new technical circulars, the requirements for maintenance scheduling change from optional to mandatory, indicating the trend of focusing on BIM adoption at post-construction stage. Nowadays, most VAR applications in BIM are limited to realistically visualizing virtual BIM models through VAR goggles at design stage. AR is rarely adopted at these stages because AR is about the combination of computer-generated perception information and existing reality. Yet, decisions are usually made inside office, where equipment like computers for design modification is available, so staff might not visit the construction stage frequently. Another reason is the existing reality, the buildings to be developed, has not been constructed yet at the design stage, and so AR cannot be applied. On the other hand, the maintenance stage offers a mature basis for AR application, because the existing reality has already been constructed. Frontline maintenance staff might superimpose the damaged object with virtual plans which illustrates the internal structure of the object, and provide details of the damage by scanning the object with mobile devices like tablets or smartphones. BAE presented similar AR applications by using photographs taken from standard mobile devices. Indeed, a number of researchers demonstrated the possibility of adopting AR at post-construction stage, for example, maintenance and facility management. Mixed reality. The combination of BIM and AR can be enhanced to mixed reality or MR. MR is the combination of AR and VR, where physical and digital objects coexist and interact in real time. For example, after identifying a building component by pointing it with a camera with built-in software, the BIM system provides feedback by giving relevant information of the building component on the screen of the camera. This is an example of combining AR and BIM. Then MR is achieved by allowing the user to add information of the reality to BIM. For example, the user may take photos of defects of the building components, as well as incorporate the photos into BIM with the cameras. Besides photos, such information reality can be reports and other annotations. MR is useful because in reports for different purposes, such as site checking and condition survey, the content needed to be backed by evidence like photos. Therefore, with MR, the user can easily pair the photos and the building components instantly on site right after photo taking to avoid further work and potential mistakes. For example, mispairing photos and the building components after site visit because of loss of memory. Hakarinen, Woodward, and Rainio demonstrated their software system to achieve MR. The system comprises of 3 modules. 1. 4D Studio provides mobile feedback to users with information from 4D, CAD, or BIM models. 2. Map Studio, locating the building components to be inspected. And 3. On-site Player, act as an interface for user to interact with AR view and add information of the reality. This is the end of this presentation and video. Thank you for watching.